अच्छा जी. So let's now continue with our discussion. We knew that gamma, which is propagation constant, is actually composed of real part and the imaginary part, where the real part is actually alpha, and this alpha is attenuation constant, as I told you before, and this is beta is actually the phase constant of any wave traveling in a lossy medium, right? So now let's have obviously it reduces to the jk, where beta is actually equal to k and sigma is actually equal to 0. This is the lossless case we discussed previously. Okay, now what are the values of alpha and what are the equations of alpha and beta? Let me write them. You can derive them and you can end up with this kind of equation. You can note them down, and it is 1 plus sigma by omega epsilon whole square. It is under the root, and minus 1 is under the big under root. So this is the value of alpha, in fact, and this is beta, where beta is actually equal to, again, omega, where omega is the radian frequency, and mu epsilon divided by 2. Likewise, small under root with 1 plus sigma by omega epsilon whole square plus 1, and this is what is alpha and beta equations, in fact. So this can be 7th and 8th equation. So far what we did is what we are considering right now is a lossless case and plane waves in a lossy medium. So plane waves in a lossy medium, we discovered that we have complex propagation constant, and that is called gamma. Okay, and gamma is composed of alpha, the real part, which is attenuation constant, and the beta, where beta represents the phase constant. Simple. Now let us again assume the example of the lossless case, and let us assume the same wave we had previously. So the same wave what we have previously was actually, if this is x and this is y and then this is z-axis, and we consider a wave which has E field in z-axis direction and H in x direction. So we have Ez component and Hx component, in fact, and the direction of propagation of the wave is in the direction of y-axis. So the direction of propagation is ay, and the components E is actually equal to Ez, which is function of y, and it is in direction of z, obviously. And then H is Hx, and it is function of y, and the direction, the unit vector is Ax. So let us take the same example and derive the equations for them, the wave equations for this particular case, in which we have the medium now lossy medium instead of lossless medium as it was before. So the wave equations are now different. We are going to have gamma instead of k, and we will then calculate the wave equations for them. So it is also the same way we calculated for the lossless case, and the end result, the differential equations governing the plane wave field components in the lossy medium are d square of Ez, obviously, and dy square minus gamma square. This time we have gamma, in fact, and Ez is equal to 0. Likewise, the other equation governing the H field is d double derivative of hx with respect to y minus gamma square hx, and it is equal to 0. So if we talk about the general solutions, the general solutions of the form Ez of with respect to y is actually equal to E1 e power gamma y plus E2 e power minus gamma y, where this can also be written as E1 e power alpha y and multiplied with e power j beta y. Since gamma is actually equal to alpha plus j beta, so we can split them, and likewise E2 e power minus alpha y and e power minus j beta y. So these are the general form of these differential equations, which are the wave equations for this particular case. Now let us go for the other one, and that comes out to be equal to h x of y. Let me directly write the end result, and I can say that this is h1 e power alpha y and e power j beta y plus h2 e power minus alpha y e power minus j beta y, whereas this portion of the wave and this portion of the wave represent different direction of the waves, different directions. So this is obviously positive y directed wave, and this is negative y directed wave.